Welcome everyone to the third micro meeting from IPPS Eastern Region. I have been selected to do the hosting for at least 2020, everybody's favorite year, but we're making the best of it and using a lot of Zoom, and it's great to see all kinds of people that are joining. I did have a few announcements real quick, just some cleaning house for IPPS. We are going to have a few more of these meetings. I'll announce them at the end as well. The next one coming up is actually going to be the IPPS North American Summit. And that's going to be a conjunction meeting between the Eastern, the Western, and the Southern regions. That'll be October 27th to 29th. And each region is going to take a half day and have an assortment of talks and tours. So keep your eye out for that. It's posted on all the social media and on the websites, and that is free as well. If you're a member, you get to look at these anytime you want. Just log in and you can look at the presentation. So that's one of the member benefits. The next micro meeting will be November 12th with Paul Capiello at Udell Gardens and Seed Collecting. After that, December 3rd, we'll have Dave Thompson and Conifer Production. December 17th, we'll have Eastern Region IPPS Foundation. Students that receive scholarships, internships, and research grants will give presentations with Brian Decker. And then in January, Brian Decker is going to do a grafting tour at Decker's Nursery. And we don't have a firm date, but that's not until January, so just keep your eyes out for all of that. So lots of stuff happening with IPPS Eastern Region this year instead of getting together and having drinks. So today we have Erik Runkle. Thank you for coming and doing this with us today. He is professor and floriculture extension specialist in the Department of Horticulture at Michigan State. And I'm in Wisconsin, so just across the lake here. And unless we have any questions right away, if anybody's having technical difficulties, let me know. I'm gonna turn it over to Erik.
Very good. Well, thank you, Liz. It's a pleasure to be invited to give a talk about LEDs and lighting in greenhouses for applications. So I'm going to go ahead and turn off my video to try to preserve the bandwidth, if I can figure that out. And then I'll reserve once we get into the Q&A, I can turn it back on. And then Liz, I'm going to be in presentation mode, in which case I won't be able to see anything in Zoom. So if there are any issues that come up or questions, feel free to interrupt me.
Sounds good. Thank you.
Okay, good. Okay, so let's get started. I'm a plant person, so I am going to get a little bit into some engineering or economics issues. I'm not an expert in any of those areas, but those can play into lighting and effects on plants and whether or not lighting is more economical from LEDs versus some other type of fixture like high pressure sodium. What I'd like to do is talk a little bit about the two major greenhouse lighting applications. The first is the photoperiodic lighting, and this is delivered to crops that are sensitive to day length. Specifically, if we're interested in delaying flowering of crops with a short day response, or promoting flowering of crops with a long day response. We will be delivering light during the short photo periods to get those sort of type responses. Typical intensity delivered is very low, so we're talking enough light that you can basically read a book, but not a lot more than that. So that's about 1 to 2 micromoles. If it was from sunlight, that would be roughly about 10 foot candles or about 100 lux for those of you in other countries. Typical spectrum delivered originally was by incandescent fixtures, then we moved over to compact fluorescence, and then more recently with LEDs. And those are usually, when they're LEDs, red with or without far red, or sometimes white LEDs. They're only practical when delivered at night and usually are on for 4 hours a day. In contrast, there's supplemental lighting, which is delivery of a much higher light intensity. And this is where the objective is to increase the growth of the crop, accelerate rooting, increase the biomass, increase the harvestable yield, or just the general quality attributes of plants. As you can see, the typical intensity delivered is much higher. For ornamentals, it's typically for 60 to up to 100 micromoles per square meter in second. The spectrum varies considerably. A lot of times, though, the LEDs are from red with either blue or white, sometimes both, and then sometimes there are other LEDs added to that. They're delivered when it's otherwise dark. So when it's cloudy, during the winter, during the night, typically the lighting has no impact or no benefit when they're turned on when it's sunny outside. So they're usually controlled by an environmental control computer. They can operate, though, most of the day, usually up to 20 hours per day, although there are a few cases here and there where you might see growers lighting continuously. So it's important that we separate these two types of lighting applications because they need quite a bit different type of fixtures and especially different intensities delivered to the crop. So I'll talk a little bit about photoperiodic lighting and the use of LEDs. These are just a couple examples of fixtures that are available. We started working with LEDs for photoperiodic lighting around 2010. That was when they were first being introduced. Conceptually, they were very expensive at the time and emitted a relatively low intensity. And since then, the prices have fortunately come down and the output has increased quite a bit. So we have an example of a Philips product on the left. That was actually a photograph taken in China. And then the photograph on the right is another company, and that photograph was taken in Michigan. And so as you can see, they typically emit kind of a pinkish cast because a lot of their output is in the red spectrum. We've done a lot of work looking at the effects of the colors of light or the light wave band on efficacy at promoting or inhibiting flowering. So I have an example here of a petunia, and I will mention that I work primarily with herbaceous crops, and so when you see examples, they're probably always going to be herbaceous. So petunia is a common long day plant, meaning it flowers faster or only flowers under long days. So when grown in a greenhouse after 6 weeks from transplant at a constant 68 degrees Fahrenheit, which is 20 degrees centigrade, under a relatively low daily light integral, which is DLI, and I'll talk about that here in a little bit. But it's relatively low light conditions that we might be receiving in a greenhouse in midwinter. On the left, we have a plant grown under a 9-hour day, and you can see it's very vegetative. And then we have 4-hour night interruption lighting, where we are turning lights on for 4 hours during the middle of a 15-hour dark period or night. We have our traditional incandescent fixture, red plus white LEDs, or red plus white plus far red LEDs. And what we have found is that there are some long day plants that really need that far red to be able to respond and flower. And so if we're looking at lighting a range of plants and we want to promote flowering of long day plants, delivery of both red and far red is the most effective. We've done work as well with other colors of LEDs, just red by itself, blue plus red. We've done studies with only blue, with only green. I just showed this slide because we also looked at a cool white LED and a warm white LED. And so cool white and warm white and daylight type of LEDs are quite a bit less expensive than these horticultural fixtures that emit primarily red with or without far red. And so we and growers wanted to know whether we could use a less expensive off-the-shelf LED like you can get at a mass retailer, or if you need one of these horticultural type of fixtures. And for a sensitive crop that, like the petunia I showed before, another example here is snapdragon, is that it really needed to include that far red light to be effective. And so there is a small amount of far red emitted by a cool white and especially by a warm white LED, but not enough to get at the type of promotion of flowering that we got if there's a fair amount of far red delivered in the spectrum. And interestingly, if you had red or blue, or even with the white, you can see that the flowering time was similar to if we didn't provide the light at all. So this is, again, maybe a more dramatic example of the effect of light spectrum. This doesn't apply to all crops, but it does apply to some long day plants, and especially when we're under light limiting conditions. So to summarize, a lot of research, probably about 8 years of research by several graduate students. We've looked at what spectrum is effective to inhibit flowering of short day plants as well as promote flowering of long day plants. And pretty much short day plants are more sensitive to light in general, and the spectrum plays a much smaller role in inhibiting flowering. So pretty much if it emits light, whether it's a white LED, a red and white LED, it's going to be effective if delivered for 4 hours during the middle of the night. If we're under low light conditions, which is a low daily light integral, fluorescents by themselves or white LEDs or red LEDs will be effective on some crops, but not others. And it really depends upon the crop, and it pretty much have to do research to determine whether it's effective on a crop. But if you're growing a wide range of species, then you're pretty much should be growing under a red plus far red LED. In contrast, when you're under higher light conditions from about mid-spring on, then the spectrum becomes less or even not important. So I want to shift now and spend most of the time talking about high intensity lighting applications in greenhouses for a couple reasons. One is that light can be a major limitation for several months of the year, especially for people in more extreme latitudes. But also the cost to install and operate lighting is much more than for low intensity lighting applications to regulate daylight. So to begin, I want to define light integral or daily light integral. We often use the acronym DLI, and it describes the cumulative number of photons that are within the photosynthetically active waveband, which by definition is 400 to 700 nanometers. So how many photons are falling in this area per meter during the period of a day? So an analogy to this is a rain gauge. And so we can measure something like rain, as in how many inches per or centimeters per second, or how many millimeters per second, or how many fractions of a millimeter per second. But really that's not a very meaningful number. We're more interested in maybe how much rain did we get within a longer period of time, such as in a day or maybe in a week. So similarly, we're quantifying how much are we getting accumulation of photons per square meter per day. And so the unit is moles per square meter per day, and you can see the abbreviations there at the bottom. I have examples for daily light integrals in the United States. There are maps that were developed originally for the United States, and I've seen them in other locations, and I'll talk about a place to get that here in a minute. But this can illustrate how the time of year and the location influences the daily light integral rather dramatically. So this is a typical greenhouse daily light integral. And this is assuming 60% light transmission through a greenhouse. So some growers may have less light transmission, some may have more. Of course, it would depend upon the glazing material, how many overhead obstructions you have, things like that. So you can see we have daily light integrals in December in the northern part of the United States that are as low as 3 to 6 moles per day on average. That continues in the Pacific Northwest in January. Contrast that to, let's say, in March in the southern half of the United States, we're already under fairly high light levels of 15 or 18 moles or even higher. When we're looking at light integrals, generally we can think that we're under light limiting conditions for a lot of crops when we're less than about 10 moles per day. And to make a very broad generalization for growing crops in a greenhouse, we typically target a minimum of 10 moles per day. But I will talk a little bit more about different minimums here in a minute. There is a relatively new website that's from a company. You can see the website is listed at the bottom, and it allows you to basically pick any location, I believe, in the world to estimate what the average daily light integral is outside during the different months of the year. And so what you can do then is use this as a pretty good gauge to be able to dial in your location, determine what is the light integral outside, and then if you can determine how much light is transmitted through your structure, you can get a pretty good sense of what your daily light integral is. Even better, some greenhouse growers have an environmental control system, and they are tracking light intensity. And some computer systems will give units in moles per day. Others will give it in some other unit, but in many cases, you should be able to convert the output into moles per day and have a sense of what your real light integrals are that you have received. But in the absence of that, you might be able to get some good information through this website. So why are we so interested in light and light integral? This is a very generalized response to how plants respond to light. So as we increase light integral, as we get a higher daily light integral, we typically see the leaves become smaller and thicker. Branching is typically increased. Stems are thicker. There's greater root growth, which of course is important for propagation. For people that are trying to flower plants, you can typically get faster flowering under higher light. And when the plants do flower, they typically have more flowers. They're larger and also sometimes have a better or deeper coloration. For people who are growing fruit, like greenhouse tomatoes, typically the harvestable yield increases with light. So you'll have more fruit and larger fruit under higher light. So obviously there's a lot of value to light, and increasing it when when light is naturally low can have some economic benefits, but of course it costs money. So just to show you a couple examples of how light integral can impact, in this case, seedling growth of salvia. So this is where we're growing plants under controlled conditions. We're keeping the photoperiod the same, the temperature the same, the humidity is similar, fertility is the same. Everything is basically the same, except we're giving plants different quantities of light. And so we have a daily light integral of only 6 moles on the left, which would again be considered a light limiting condition. Integral of about 10 moles, which would be about our minimum threshold, and then a moderate light intensity of 16 moles per day. And as you can see, there is more root growth as you go from left to right, as you increase the light integral. The stems are a little bit shorter, leaves are a little bit smaller and maybe a little darker green, and the stem is a little bit thicker. And so generally this is a higher quality seedling. It's ready for transplant earlier, and it's a little more compact. And so I think a lot of people would consider that this is a better plug growing under high light conditions than under lower light. Over the years, we've also done a lot of work looking at sticking cuttings and how the daily light integral can influence adventitious rooting of herbaceous plants. We have not worked with woody plants, but I would expect very similar trends. So this is in a propagation greenhouse with high humidity. We would have bottom heating. Air temperature would typically be about 73 degrees Fahrenheit or 23 degrees centigrade. And we can see plants grown under 6 different light integrals, ranging from a really low integral of 1.3 moles per day, increasing to high light conditions for a propagation greenhouse of about 11 moles per day. So as the photos show, and as the root dry mass numbers at the bottom indicate, you get faster rooting basically as you increase the light integral up to some point. Of course, at some point, if you deliver so much light, you're going to be stressing the plants, you can cause a negative reaction, but we typically don't see that beyond until at least 10 or 12 moles per day. What we really want to try to avoid, though, are these really low light conditions of 1 to 4 moles per day, because this is where it can really take a long time for these plants to be in a propagation environment. And of course, the longer you're in a propagation environment, the more potential there is for challenges with managing pests, with fertility, and other aspects that can crop up. So one of the questions then is, you understand how much light you have, and then the goal is to determine how much light you need to add to get to your desired minimum daily light integral. And so this is going to be quite situational. It's fairly subjective, depending upon the crops that you're growing and then other environmental parameters. And so these are just some examples of, just to give you some ballpark numbers. And again, they're fairly subjective, but typically early during propagation, stages 1 and 2, when you're basically hardening cuttings, trying to get them to callus, or with seedlings when the seed is germinating and maybe the cotyledons are unfolding. You don't need a lot of light. You want some, of course, but it's not considered a situation where you want to give the plants a lot of heat or stress. So a minimum 4 moles per day is suggested, and about twice that in later stages of cutting growth or seedling production. Annual bedding plants and leafy greens and herbs, we typically recommend a minimum of 10 moles per day. Herbaceous perennials a little bit higher. And then cut flowers and fruiting vegetables would typically be the highest type of light crops, and that's because the quality and the quantity of those increase with light. And in fact, even 15 moles of light would be relatively low for fruiting vegetables. We've done a fair amount of research looking at the light spectrum and its effect in supplemental lighting. So we've looked at white LEDs, combinations of red and blue, sometimes with far red, and then comparing them to the high pressure sodium. And I haven't talked much about high pressure sodium yet, but it is still the most common fixture that's out there for greenhouse high intensity lighting applications. What I want to do is kind of go through some of the things to be on the look for when we're talking about LEDs, because LEDs are expensive, right? And that's really the biggest limitation towards implementation of LEDs in greenhouses. And so naturally, people are trying to look at lower cost fixtures. And it's tempting that when you see a product that may be even marketed to greenhouse growers, to look for products that are a little less expensive. And so there might be examples of companies that have developed light specifically for gas stations or street lighting or parking garages. And generally, those fixtures are not made to tolerate tough conditions that you might see in a greenhouse, such as really high temperatures or high humidities. And so when you see LEDs that are marketed for different applications, they're not necessarily conducive to horticultural lighting. Another challenge with these other types of fixtures is that getting uniformity is virtually impossible with these fixtures. They're typically designed to be installed much higher above the crop than you could install in a greenhouse. And in many cases, I think the uniformity of light is almost as important as the actual intensity of light delivered. Another challenge is to be aware of excessive shading from fixtures. Of course, if you're operating these under a gas station, you don't really care what sort of shading there is because it's probably under a roof already. But you want to minimize shading in a greenhouse so you're not reducing solar transmission. So I want to talk about basically the big question is whether someone is going to install lighting or retrofit their greenhouses with either more efficient high pressure sodium fixtures or if they want to consider LEDs that are more energy efficient. So these are many of the major considerations, certainly not exhaustive, but the things that I'm going to talk about here today. One is the electrical supply, how much is available currently and whether you need to bring more electricity into your operation. What is the uniformity of the intensity delivered, whether it's by high pressure sodium or LED? What sort of light spectrum do you choose? And considering, of course, plants, but also people that would work in that environment. How does temperature influence the choice of a fixture and how it might be different under a high pressure sodium versus an LED? I'm going to talk a fair amount about the efficiency of a fixture, which we refer to as the lamp efficacy. And this is basically the efficiency of a fixture converting electricity into photosynthetic light. I'll talk briefly about the longevity of a fixture and whether it needs maintenance, but then ultimately it comes down to cost. And so what is the cost of the electricity? How many hours do you typically run the fixtures? And then what is the cost then to operate the fixtures and of course to purchase and install them? So I'll run through some of these and especially the latter ones in a little more detail. So electrical supply. Do you already have enough power to your facility to install the lights that you want? If you don't, then what are the costs to bring more electricity to your facility? And because LEDs consume less energy than high pressure sodiums, you may not need to bring added power to your facility, or you may need to bring less than if you were to use high pressure sodiums. And the cost to bring electricity or more electricity into a facility can be rather significant. And so this can be a game changer if you have to bring in more electricity for one particular fixture over another. What sort of intensity in uniformity or uniformity of intensity are you getting from a different type of fixture? So when we look at LEDs or high pressure sodiums, working with a lighting company or a lighting supplier, they should be able to provide you with a lighting map. And the map basically tells you a couple things. One is, and this is an example here on the screen, is what is the positioning of the fixtures? So how are they spaced? How are they oriented? And how many do you need in a certain growing area? And then what is the predicted intensity of the light over that area in the greenhouse? In this case, these numbers are in micromoles. And we basically told this company that we wanted a lighting plan that delivered an average of 80 micromoles per square meter in second. And as you can see, they were relatively good at delivering our desired intensity. Of course, there are going to be some hot spots directly under the fixtures, and then a little bit lower as you get farther away from the fixtures. But overall, it was, we thought, fairly effective, especially for a small greenhouse. The uniformity, of course, should be better when you can hang fixtures up a little bit higher. So a high-roofed greenhouse can have a better uniformity than a low-gutter greenhouse. But also, when you have larger areas, you should be able to get a more uniform intensity. And typically, the goal will be to get something within a 15 to 20% variation in light intensity. Of course, the more uniform, the better, because that means the crops will be more uniform with better uniformity of light. So what about the light spectrum and the distribution of that light? If you look at horticultural fixtures, most of them emit either a purplish or a pinkish light. And this is because they primarily include red and blue LEDs for a purplish fixture, or red and white LEDs for a fixture that emits more of a pinkish light. There are other examples, however. There are fixtures that emit only white or mostly white. There are also fixtures that maybe emit red, white, and far red. Those would probably be for more specialized applications. Or if you're in environments where maybe you want a lot of blue light, or where you're working, where you're in an environment where you have a lot of people working. And as Liz and I were talking here at the beginning, is before the seminar started, is that the spectrum can have an effect on people. And so when you have only a red and blue LED, it really casts more of a purple light that can be a little bit challenging for people to work in. We have a lot of fixtures that emit that have red and white LEDs. It emits more of a soft pinkish light, which I have not personally found objectionable. Whereas if you have a lot of people working, you may consider more of a whitish light. So anyway, to consider obviously the spectrum and the effects on plants, which I'll talk about here in a second, but also to consider how many people are going to be working in that environment, especially when the lights are on but it's dark outside. Okay, so we and a colleague, Roberto Lopez here at Michigan State, have done a lot of work looking at the light spectrum and the effects on supplemental lighting and effects on the crops. Based on our research, basically, we have found that when the light integral is low, for example, less than 8 moles per day, the spectrum can have an effect at regulating extension growth and the pigmentation of leaves. So for example, we know that blue light has a big impact on suppressing extension growth in supplemental lighting and on increasing the coloration. So leaves that are typically more of a purplish color will be purple with a high percentage of blue light compared to a low percentage of blue light. We can also see plants that are a little more compact under high light intensities from blue as opposed to low blue. However, we found that when we're growing plants under more sunlight, when the daylight integral is higher, that the spectrum has a diminishing impact on the growth of the crop. So if we're already getting a fair amount of sunlight, let's say we're getting 12 moles per day, and we're only adding maybe 3 or 4 moles of supplemental lighting to that, basically the spectral effects are washed out by how much sunlight we're already getting. What about impact of temperature and heating? And I've heard a lot of growers say they prefer using high pressure sodium lamps, partly because they like the warmth of the plants. They like that long wave energy that's emitted, and the crop is therefore a little bit warmer. There's been some research done to quantify the impact of the different lights on crop and plant temperature. And several studies have found that on average, plants under high pressure sodium lamps are about 2 to 3 degrees Fahrenheit or 1 to 2 degrees centigrade warmer than under LEDs. Of course, this will depend on the intensity, but the consequence is that plants can grow slightly faster under high pressure sodium. However, high pressure sodium lamps are now typically less efficient. compared to especially newer LEDs. And so while it does serve to increase the temperature, which can be desirable, it's typically considered an inefficient heating method because the cost of electricity for many places is more than getting BTUs from natural gas or some other fuel type. So I want to talk a fair amount now about fixture efficacy or efficiency. This is not something that we can individually go out and measure. It's not something that we can use a sensor to get the number. It's really something that you need some sophisticated equipment and expertise to be able to come up with these numbers. Just in the last couple of years, we've been fortunate that horticultural lighting companies have been quantifying this and actually publishing this metric for their different lighting fixtures. So the efficacy of a lamp refers to basically how much total light is emitted by the fixture per amount of energy that's consumed. And so to measure the total output of a lamp, you really need an integrating sphere, which is basically this is a picture taken in a laboratory at Rutgers University, where you put the fixture in the middle of it, you turn it on, you close the dome, and then there's a sensor in there that's basically integrating all the light that's being emitted and quantifying that. And at the same time, they are monitoring how much energy is being consumed to emit that light. And so you need this expensive equipment, and it's, again, not something that we can measure. There are testing labs that have these facilities. Many of the major lighting companies have an integrating sphere, as well as a handful of academics. So to determine the efficacy, as an example, if a lamp emits 600 micromoles per second, so that's the intensity of light delivered per second, and that's of photosynthetic photons, so from 400 to 700 nanometers. And in doing so, it consumes 300 watts. A watt is a joule per second. You can do the math, dividing basically the micromoles divided by the joules, and you get, in this case, 2 micromoles per joule. So this would be the example of this fixture in the energy efficiency. And so the higher the value, the more efficient the fixture. Now, when we look at individual LEDs, the efficacy varies by the color type. So as of today, at least, the most efficient LED type that we sometimes see in horticultural lighting is far red. Now, far red is by definition outside the range of photosynthetically active radiation. But we know, and there's increasing evidence that far red can have both direct and indirect effects in increasing plant growth. It can also, though, have some negative effects such as increased elongation and triggering of some of the shade avoidance responses, which in some cases is desirable, but in many cases it's not. The next efficient type of LED is a red LED, and that's the primary reason why we see horticultural fixtures emitting a lot of red light. Next is a blue LED, less efficient than a red, but typically then a little more efficient than a white. So white LED is actually a blue LED with a phosphor coating over it. And so whites are always going to be slightly less efficient than a blue LED. And so for these reasons, when we look at horticultural lighting fixtures, pretty much always the most efficient lighting fixtures for LEDs will be those that primarily emit red and a little bit of blue. And as you increase the amount of blue or you increase the number of white LEDs on a fixture, the efficacy is going to go down. There are green LEDs available, but they are very inefficient. And so you typically do not see them for production modules for horticultural applications. These are some examples of, in this case, 3 high pressure sodium fixtures and the total amount of light that's emitted by a fixture, as well as the efficiency or the photon efficacy. And then 6 examples of LEDs that I subjectively chose just for illustrative purposes to see how they might range. The first one then is a 400 watt high pressure sodium. It's got a magnetic ballast, and it is still probably one of the most common lighting fixtures that are being used in greenhouses today, at least in North America. You can see they emit about 416 micromoles per second, but the efficacy is quite low at 0.9. When we move from a magnetic to an electronic ballast, and as we increase the wattage, we typically see an increase in the efficacy as well as the light output. So if we look at the double-ended high-pressure sodium, the third on the list, the Gavita Pro, you can see that this emits a lot of light, 1,800 micromoles per second, and the efficacy is around 1.7, and some are approaching 1.8. Now, when LEDs were really starting to enter the mainstream horticultural area about 4 years ago, we saw that the most efficient LEDs were as effective as the most efficient high-pressure sodium. Fortunately, that has changed. LEDs have advanced significantly just in the last 4 years. And you can see that quite a few fixtures have a metric efficacy of at least 2.5. Some are at 3, and there are even some now that are even above that. And so we're on the cusp, if not already, at the point of having LEDs that are twice more efficient than the best high-pressure sodium. This is a slide that shows basically the impact of the how hard you drive an LED, how it influences the efficacy of an LED, as well as a comparison of the different LED types. And so here at the bottom, we have a white LED. You can see the efficacy is somewhere around 2.5 to 3. It's higher as you run it basically at a lower current density, and as you run it progressively hotter, the efficacy begins to come down. And you can see similar trends for blue, red, and far red LEDs. So there's a fairly big gap between the blue and the red LEDs, and again, that's one of the reasons why we see a lot of fixtures that emit a high percentage of red light. And then the far red are the most efficacious, but we generally don't see many of those. We don't see many fixtures that include far red LEDs. And then you can see what these theoretical maximums are for a blue and white LED, as well as a theoretical max for a red LED. So if you think of what the metrics were before for the most efficient LEDs, you can see that, for example, a Philips or Signify fixture that emitted about 5% blue and 95% red had about an efficacy of 3.0. If you look at what these theoretical maximums are, if you had a lot of red, you might be able to get, efficacy that might be closer to 4 than to 3. It's, of course, we don't know what the efficacy will be for fixtures as opposed to individual LEDs, but we're at least beginning to approach these theoretical maximums. There still is some room for growth, but I think the efficacy rate increase is going to begin to diminish here in the next several years. So as the power to LED increases, typically the output increases, and so fewer LEDs are needed to deliver a certain light intensity. So this can decrease the capital cost of the fixture or the purchase price. The downside, though, is that as you increase the power, the efficacy begins to decrease as well as its lifetime. And so you can get maybe a slightly cheaper LED because it has fewer LEDs on the fixture. But the downside is it may not last as long, and the efficacy will begin to go down. And so you have these trade-offs that you need to determine, or the companies are having to decide how hard do you drive it, how efficient is it versus what the capital cost might be. Some other considerations, one of them is whether there are utility rebates available. It will vary quite a bit geographically, but in some locations, especially in the United States, I know that there are rebates available from utility companies for improved energy efficiency. So if you currently have a 400 watt high pressure sodium and you can substantially reduce your energy consumption by switching to LEDs, there may be some good incentives to support that. And that incentive may be sufficient to influence one lighting decision over another. When you choose a lighting fixture, whether it's an LED or a high pressure sodium, the goal is to minimize shading of the fixtures and any drivers that are needed so that you're casting as little shadow to the crop as possible. Ideally, you want LEDs that are, or any fixture that is easy to install. And an advantage of an LED is they're typically quite a bit easier and certainly less heavy and bulky to install compared to a high pressure sodium. How long does a fixture last and whether it has a warranty, and then whether or not the fixture meets the technical specifications to be considered a qualified product by the Design Lights Consortium. So what is the Design Lights Consortium? Well, it's basically a non-for-profit organization in the United States and Canada whose goal is to basically optimize energy. They focus on the effects of lighting for people, and then more recently, lighting for plants. It's a website here available to learn more about DLC. It's designlights.org. But I think it'll be of interest for people who are even not in the United States because it gives you maybe a clear understanding of what they think are the minimum specifications for an LED to be considered energy efficient as well as able to tolerate horticultural conditions such as in a greenhouse. These are just some of the technical requirements for a fixture to be considered as a qualified product. So I talked a little bit about the photon efficacy or the efficiency of a fixture. And they're saying basically the minimum should be at least 1.9 micromoles per joule. So if we go back, let me go up a couple slides here. If 1.9 is the minimum, then you can see all 6 of these examples of LEDs are qualified and therefore easily surpass the minimum. There is some talk that the 1.9 metric will increase in the future because they do want to, because efficiency of LEDs continue to increase, they do want to be able to have fixtures that are considered energy efficient, not only today, but what that might mean in the future. What about the light output and how long does it last? And so they have a minimum Q90 of 36,000 hours. So Q90 refers to how many hours does the fixture need to operate before its light output has diminished by 10% from the original installed light output. So basically, once you've run the fixtures, they should last at least 36,000 hours before 90% of the light, before you get less than 90% of the original light output, if that makes sense. So anyway, this is a very long time. They're saying basically that you should be able to run these fixtures at least 36,000 hours before you've seen a 10% decrease in light intensity. If the drivers and the fans, if there are any, if it's an actively cooled device, they should last at least 50,000 hours. They should have a 5-year warranty, and they should receive some sort of safety certification. And so they should be safe, they should be able to tolerate horticultural conditions, they should last quite a long time, and they should be relatively energy efficient. There are a few other things that are required to be a qualified product, but these I think are the major ones from an application standpoint as a user. Now, LEDs are not perfect, so any emerging technology will have its problems. And over the years, I've talked with growers who have had some challenges along the way. And so just some of these are potential problems just for people to keep their eyes open. So there is a surge in demand for plant lighting, certainly in North America, but we're seeing more and more crops that are being grown in greenhouses, and therefore demand for supplemental lighting has increased substantially. And as a result, some companies are better than others at responding to inquiries, whether it's to get a lighting map for potential purchase or customer service after you have received the fixtures. Sometimes you talk with companies and they don't have plant lighting expertise. And so there are a lot of general lighting companies that have gone into plant lighting. Many of them do have experts and know about plants and how they respond to light, but some don't and may not be able to answer your questions well as it relates to plant lighting. There can be long delivery times and shipment delays, and we have seen this. We've experienced it ourselves. I've heard it from many companies where they finally decide to make a purchase and then they realize they may not get the fixtures for 3 or 4 months or 6 months, whatever the backlog may be. There have been challenges where insufficient number of accessories have been purchased and they need to then go back and order more, or they ordered them and it wasn't fully shipped. There have been, I would say, uncomfortably high failure rates for fixtures or drivers. So I've heard companies report 5% of fixtures going out within a year. And so how is the company going to be able to, how will they respond to that if that were to happen? Unfortunately, there are companies that go out of business. And so if they are no longer in the lighting world and you have fixtures that begin to fail, I'm afraid you're out of luck. And so doing your best to pick a company that you think will be in business and be able to support their product in the future, I think goes a long way. But of course, that's impossible to know. And then once you have an installation, will there be similar fixtures available in the future? So if you have fixtures that begin to go out down the road and you want to replace them, you may be challenged to find a similar fixture. So the light output could be different. It may be higher than what you had before, which could create a hot spot of lighting. Or it could be the spectrum is a little different, which could create a slightly different plant response. So just something to keep in mind. So then ultimately, a lot of these decisions come down to costs. So if you know what your electricity rate is and how many hours you anticipate using lights, you can begin to calculate what is the electrical cost to run fixtures based upon energy efficiency of the different options available. It depends also then how many hours you're going to be running these fixtures. So young plant growers typically only use fixtures seasonally. Some only use them maybe from January through March. And they might only use them 1,000 to 1,500 hours. Whereas others may use fixtures 6 or 8 months of the year, depending upon the crop they're growing and their location. So knowing how many hours you run your lights each year can be informative. So when you make a decision that you want to install lights, whether they're high pressure sodiums or LEDs, it's best to contact companies or their suppliers to obtain a customized lighting map for your specific operation, given the dimensions of your greenhouse and how much light you want delivered to the crop. And they should be able to give you a lighting map and then a quotation for the price to deliver that desired light intensity. Again, the quotation should be specific for your facility, and they really should be using micromoles per square meter in second. That is the appropriate metric for instantaneous light for plant applications. If they use lux or foot candles or something, those are biased towards the human eye, and they're really not appropriate units to be using for plant lighting. The company should provide you with this lighting plan and details on the light spectrum. They should tell you the efficiency or the efficacy of the fixture, the expected lifetime, in other words, what is the Q90, and then whether there are any warranties. And if it's a DLC listed product in the United States and Canada at least, then it should be able to meet all these minimums because these are requirements. Something else then to consider is how many fixtures can you attach to each driver. And again, this can have effects on installation ease, as well as the more drivers that you need, the more shading that will be cast on the crop below. So I'm very hesitant to put this up there because I'm not an economist, but I think sometimes just to show you that it's not that difficult to come up with a real simplified economic analysis of whether you go with one type of fixture over another. So these are some numbers working with a grower a couple years ago, so they're a little bit dated. But in this case, the grower's electricity price was 12 cents a kilowatt hour. They anticipated using the lights for quite a few hours of the year, so 2,500 hours per year, which is certainly on the high side. Their comparison then was a high pressure sodium. So ultimately was their question, do we go with this LED? Even though it's more expensive, will it be a wise investment compared to a high pressure sodium? So they obtained lighting maps from 2 different companies, which told them how many fixtures they needed to deliver that desired light intensity, and then how much it would cost to deliver that intensity. So in this case, the LEDs were about 2.5 times more expensive. The installation for the high pressure sodiums would have been $60,000 more because more electricity was needed to be added to the facility. And in this case, the grower anticipated an energy rebate if they went with LEDs, which would reduce the purchase price by about $18,000. And then to look at the operation costs. And so again, these are a little bit older numbers, but they ran the numbers about how many watts are consumed per fixture. converted that into total power draw, what their electricity price was, and how much electricity they consume per year. They then added in a small amount for bulb replacement because they would need to replace the bulbs a few times, several times probably in the lifetime of one LED. And you can see that just looking at a very simple payback, not considering interest or depreciation or things, that their investment would be returned in under 3 years. So again, this is a very simplified analysis, but it gives you a sense of how you can run some numbers yourself and determine what options out there are more economical for you. So with that, I want to conclude here with just some slides for more information on plant lighting if you're interested. This is a book I co-edited with my colleague that focuses on light management and controlled environment. It has 20 chapters with 18 chapters with 20 different authors, primarily by experts in North America. It's available in print and digital versions through Amazon. We also have a lot of articles on our floriculture and greenhouse crop production website. There's the URL at the top, or if you just type in MSU floriculture, you can probably get to this page pretty easy. We have a lot of resources, which are primarily trade magazine articles in which we provide the PDFs at no charge. And quite a few of these articles are written on the topic of lighting. And last but not least, I'd like to acknowledge different funding agencies and lighting companies, as well as private growers that have supported a lot of the research that I presented today. So with that, I thank everyone for your attention, and hopefully we have time if there are any questions.
Awesome. Thank you, Eric. That was super thorough. You're definitely the aficionado of LED lighting. That was a lot of information to cover. We do have a good amount of questions. I'm not sure I introduced myself in the beginning. I'm Liz Dunham. I work at a tissue culture lab. I think most of you know who I am at this point. We do use all LEDs here. They're all white. We did get a grant from our local utility, so if you're interested in doing this, definitely contact those people and see if they have a program for you. Ours was really simple because we just fit in the bulbs to our old ballast, and that made it cost efficient and just super easy for us. The best benefit that we had here is the lower heat load that we have from the LEDs versus the fluorescent lights. So I'm going to go ahead and read some of these questions. Some of them may be kind of a review, but you gave us so much information, I think that's going to be okay. Ronald asked, what's the most practical way to measure light intensity?
Quantum sensor. Quantum sensors are developed specifically to measure photosynthetic light. There are much less expensive light meters available that measure in foot candles or lux. For sun applications, those are fine, but if you're working with LEDs, you really need a quantum sensor because they have the filters that are needed for the readings to be accurate. If you took a $30 light sensor and tried to use it under horticultural lighting, the numbers would be way off. So quantum sensor is the best unit. They're typically a minimum of $300. So they're quite expensive, but it should last you quite a long time.
Okay, great. That answered that question and the other one that came after it. Let's see here. Which color is effective to root development? So far, what we have seen is that what's most important is the amount of light that's delivered to the crop and not the color of the light. My colleague, Roberta Lopez, has done more work with lighting and propagation, and it's rare when we see an effect of the spectrum of the light on the rooting. It's really much more related to how much light is given to the crop than the spectrum. So at this point, I can't say that color matters. Okay, yeah, that's what I've seen here. You know, we have a lot of propagators here, so everybody wants to know about rooting.
Sure.
Let's see here. Keith asks, we talk a lot about light for cuttings and rooting, but is there a better response for seeds to germinate and grow under LED lights?
So there are, of course, some seeds that need darkness, and then those that need light. You know what? The color of the light really would only have an impact if you're at really, really low light intensities, as in fractions or as in a micromole, which unless you're in a completely enclosed environment, the spectrum would not matter. Now, if you're in a completely enclosed facility and there's no sunlight, and you're delivering very low light intensities, then red would be the most effective. But other than that, as long as there's red in the spectrum, really it doesn't play a role. Again, unless you're in some very isolated laboratory under very low light conditions.
Okay, thank you. Let's see here. Kyle asked, if you are trying to avoid stem elongation in cuttings, would it be better to have a higher blue to red ratio?
Yes, it would. But the impact of the spectrum is really only noticeable when we're under low light conditions. So if you're getting less than 7 or 8 moles per day, then more blue would be better. Now, once you get to maybe 20, 25% blue, we seem to saturate responses. So it's not like you need massive amounts of blue. Now, the other thing that we've noticed, and it's funny, we've done a lot of studies over the years, and I've kind of come to the conclusion that light intensity trumps light quality. And so if you're only delivering a low intensity of supplemental lighting, then the spectrum is more important. But if you're delivering, let's say 100 micromoles, then the spectral composition is less important. So anyway, when in doubt, add a little more blue, you'll get a little bit stronger response in suppression of elongation and more compact rooting, or more compact shoot growth. But really that's noticeable during the winter months and much less so as we get into mid to late spring.
Okay. Awesome. Let's see, a couple more questions. We're almost out of time. John asks, some lighting companies are reporting efficiency around 4.1. I have heard that this is largely exaggerated. Is that true?
That's a good question. So it's not uncommon for companies to publish a number that's not backed by an unbiased source. And so one of the reasons I have suggested the Design Lights Consortium is they require testing from a laboratory to support the efficacy that they give. So actually just recently I saw a company that was advertising something like 3.6, and yet I didn't see it listed on the DLC website until much later, and then on the DLC website it was something like 3.2. And so I would say, you know, they might, and I'm not saying the company is necessarily lying. It might be that they created conditions and they got this value, but maybe it wasn't these very controlled conditions that might exist in a lighting laboratory. So the numbers that are on the DLC website, I think you can pretty much bank. But if they don't have any sort of information to support it from an independent testing lab, then I think it's good to be skeptical. Having said that, I've started to see values that are in the low 2s and even the low 3s, even into the middle 3s just very recently. So I don't think we're at 4 yet, but sorry, one more thing. I've also seen a company just report a whole number. So they might put an efficacy of 2. Well, and this was a couple years ago. Was it 1.6 and they rounded to 2, or was it 2.4? Anyway, so they might give out a number 4, but it could be 3.55 and they happen to round up to 4 just to give a round number. So you would want to see at least 1 decimal. So like a 3.6 or a 3.2 or whatever, and not a round number.
Sure. This question kind of goes along with that. What are tried and true lighting brands you would recommend to a grower?
I have to be careful.
Right, exactly.
Yeah, so
broad here, I guess.
Yeah, you know, I would pick a company that has a pretty good presence that you've heard about. That's probably been in business for several years, has some background in lighting, a company that you can be somewhat comfortable to be in business in 5 years. preferably maybe even a multinational company. Now, that doesn't mean that a local lighting company can't make good fixtures. I don't want to say that. It's just that, if they don't have this track record, then you have to be a little more skeptical. And so, companies that you see that give webinars, that you see them advertise, and talking with growers who have experiences is really valuable. There's a grower in Michigan who actually decided that he's a very large grower, and instead of making one big purchase, he thought, well, I'm going to buy a few fixtures from 3 different companies, compare them himself, and determine what he liked the most. And so that was one way to kind of get his feet wet without making a huge investment. And then when he did make a big investment, he felt like he had more confidence. So yeah, I'm hesitant to name specific companies, but hopefully that is a little bit of helpful information.
Yeah, I think that's helpful. Let's see here. I'm just going to do 2 more. Is there a standard distance, at least, using LED and lighting? I'm assuming they mean distance from plants.
Yeah, there's not, and it really depends on the type of fixture. So when I talked about efficacy, I also mentioned or included data on how much light is output per fixture. And so it'd be kind of analogous to whether you had a 400 watt sodium or a 1,000 watt sodium, where the 1,000 watt sodium, you would need to be several feet farther away from the crop than a 400 watt sodium. So it's really going to depend upon how much light is emitted by the fixture to determine the distance. But, you're typically at least 5 feet away. And for a higher intensity fixture, you probably want to be at least 7 to 8 feet away to get a fairly good uniformity.
Let's see here. We'll go with one more question. And you might have answered this. Is there a major cost difference for only white lighting versus red and blue lighting, for example?
So white LEDs are certainly less expensive. Surprisingly, though, the costs from what I have seen are not necessarily cheaper with mostly white versus red and blue, or red and white and blue, or red and white. And so it's really something that you need to do, to try to get lighting plans. Now, at the fluorescent tube level, if you're talking about something that also has commercial, like a general application for lighting, you might find that white LEDs are much cheaper, like to replace a fluorescent tube like the fixtures you have, Liz, versus a red and blue fixture. So the white fixture in that case may be quite a bit cheaper, but if you're talking about a high intensity fixture, then you know what, they're actually fairly, from numbers that I have seen, whether it's mostly white or mostly like a red and blue, the prices are actually within the same ballpark.
Okay, great. I think that's all the questions for the most part. There was one question that came in, and I can answer that. Will this video be available to rewatch later? So IPPS, it is a membership with dues, and if you're a member, then you can rewatch it whenever you want. We'll have some links that come out with the newsletter. I don't believe they're going to be available if you're not a member. So become an IPPS member. We're going to do a lot more of these. It's not that expensive, and you'll get all your questions answered. Our motto is to seek and share. So if you have a question and you're a member, we're going to answer it to the best of our abilities. And it's an international group of people that know what they're talking about when it comes to plants, and just a really nice group of people to talk to and hang out with, hopefully in person sometime soon. So with that, I'm going to say thank you so much, Erik, for doing this for us. I think everybody learned a lot. I know I did. And I'm assuming that you're available for questions afterwards. You have an email that's published.
Yeah. Yeah, type in my name.
Yeah.
Oftentimes I have an article. If people have a question, it's actually interesting to get questions, because that's how I formulate what to write articles about. So yeah, if people have specific questions, I can try to answer them as time allows, or I can maybe give them a resource for more information.
Awesome, great. And like I said at the top of the hour here, we are going to have a whole bunch more micro meetings. The goal is to do one a month, and we get great people like Erik to come and do this kind of stuff on a wide variety of topics. If there's a topic that you would like us to do a talk on, email IPPS, and we will see if we can get that going. November 12th is the next micro meeting, and that's with Paul Capiello at Udall Gardens and seed collecting. And like I said, there should be one every month. I think we have 2 in December. We're also going to have the North American Summit, which is the Eastern, Western, and Southern coming together in October 27th. I believe it starts, and then 3 days in a row there. We'll all be presenting tours and talks at that point. And so far, this is all free. I think we're going to make it free until the end of the year. So go ahead and take advantage of that and tell all your friends that like plants. And I think that's pretty much it for today. So thank you everybody for coming and attending this micro meeting.
Thanks, Liz. Thanks, everyone.
All right. Thanks everybody. Bye-bye.